Hey guys, this is the delayed video about light in the electromagnetic spectrum. This is for students who are not able to participate in the Google Meet when I did this live, or who just need a quick review of it. So we'll go through this fairly quickly. So in this video, we're going to talk about what light is, and where it comes from. We'll talk about the dual nature of light, which is the concept that we need to be familiar with, what color is, and finally, the electromagnetic spectrum, which will be an introduction to the lab activity that you need to do. So first, what is light? Light is what we call an electromagnetic wave, and it's actually an oscillation between an electric field and a magnetic field. It turns out that electricity and magnetism are two sides of the same coin. As you know, if you take a wire and you wrap it around a nail and then run an electric current through that wire, you can pick things up with a nail because it becomes magnetic. So an electric current can produce a magnetic field. And likewise, you may not be aware of this, but the way we generate electricity is to move magnets near wires, and the moving magnetic field pushes electrons. So magnets can produce an electric field or an electric current. So this happens naturally and very easily when a magnetic field appears. The growth of that magnetic field produces an electric field. And when that electric field grows, it produces a magnetic field. And when that magnetic field, and the cycle just continues. Now, conservation of energy still applies. So when the magnetic field appears, it transfers its energy into the electric field that it creates. And when that electric field appears, it transfers its energy into the magnetic field that it creates, and so on. So it oscillates from electricity to magnetism and propagates in one direction at the speed of light. And that's what light is. It's a way for energy to travel through open space. Okay, now next, so light is a type of wave called an electromagnetic wave. Now, at some point, we have to talk about the dual nature of life and why not light. So why not now? So sometimes there's some experiments that we can do that prove very conclusively that light is a wave, and we'll see some of these in this unit. And there are other phenomena and experiments that prove very conclusively that light is a particle, that it comes in discrete packets of energy. And this is strange that we have convincing evidence, compelling experiments that both of these are true. So the dual nature of light, that phrase means that light is both a wave and a particle. And I know that sounds strange, but it's true. And it's actually our first glimpse into the quantum realm of reality. When things get very, very small, they become uncertain. And things which are objects behave like light. Behave like waves. And waves behave like particles. So for example, electrons, which we know are discrete particles, we can catch one, we can weigh it, we can measure its charge. If you look at it very closely, it becomes a wave. So yeah, dual nature of light. Light is both a wave and a particle. Okay, let's see. We don't need this one right now, so we'll come back to that another day. Now, where does light come from? Light comes from many sources, but generally speaking, it comes from moving electric charges. So an electric charge moves, that kicks off the cycle. It makes a magnetic field, which kicks off an electric field, and so on. And the result is a beam of light. Now, the easiest way to understand this, and really the most common, is in an atom. Imagine this is a hydrogen atom. There's one proton in the nucleus, and as you know, there's electrons, one electron, which is going to orbit it. Now, as you also know, electrons can settle in any of several energy levels around an atom. So normally, the electron will be at the lowest energy level, and that's where it stays. But if we come along and we bump into this atom, we might be able to jostle this electron enough to lift it up to a higher energy level. This is sort of like hitting a baseball and a pop fly, and we make it rise up. And if it goes high enough, it may land on top of the press box up in the second deck of the stadium. And now it's higher than it was before, and it's fairly stable up there. But we had to give it energy to lift it up that high. And the same thing can happen to an electron. If we hit it, we can knock it to a higher energy level where it will remain stable for a little while. But the electron's not going to stay there for very long, and it will want to drop back down to its lower energy level, just like that baseball up on the press box. If somebody bumps it, it's going to roll off the edge and fall back to the field again. Now, we have to give the electron energy to lift it to a higher energy level, just like we have to give the baseball energy to lift it up to the press box. And conservation of energy is a thing. So when the electron drops back down to its lowest level, it has to release that energy in some way. And the way it does it is by spitting out a little beam of light. Okay? The electron dropping from high energy to low energy, that's a moving electric charge, produces a magnetic field, which sets off the cycle, and the light streams away at the speed of light. Okay, so where does light come from? Usually from electrons dropping from high levels to low levels. Next, we're going to move on to, let's see, electromagnetic waves. Yes, explanation of electromagnetic waves. They are waves. So just like all the waves that we studied in the last unit, each wave has a speed, it has a wavelength, and it has a frequency, which means that the wave equation is still a thing when we're talking about light waves or electromagnetic waves. Okay, so that's one thing that's similar. Now, electromagnetic waves are different than the waves we studied in the last unit. For one thing, they don't need a medium. Electrical fields and magnetic fields can exist on their own. They don't need to exist inside some other substance. So electromagnetic waves, light waves, can go through the vacuum of space. They can travel through the vacuum. Mechanical waves can't do that. They need a medium. Mechanical waves do. Okay, second, electromagnetic waves are much faster than any other type of wave. They move at 300 million meters per second, or 300,000 kilometers per second. This number may seem more familiar, 186,000 miles per second. That's a long, long way. The light wave can get to the moon in just over a second. That's very, very fast. This number over here, 3.0 times 10 to the 8th meters per second, that is the speed of light in a vacuum. Now, it seems like a strangely round number, but it's just a coincidence. That's what it turned out to be. Okay, another thing about electromagnetic waves is that the amplitude of light waves is always the same. Now, why is this significant? So when we talked about mechanical waves, like waves in a rope, the amplitude of the wave indicated how much energy the wave was carrying. A big wave on the ocean will knock over a boat. A small wave on the ocean will just make the boat rock a little bit. If we're talking about waves in a rope, if I wave the rope just a little bit, somebody holding the other end of the rope, their hand will shake just a little bit. If I shake it a lot, so the big waves with large amplitudes are going down the rope, it's going to shake their hand a lot. So big amplitude means lots of energy when we're talking about mechanical waves. But light, electromagnetic waves, the amplitude is always the same. So how does energy manifest itself? Well, it happens with higher frequency. So a light wave that has more energy has a higher frequency and consequently a shorter wavelength, as we'll see in just a second. This is what I want you to remember. High energy light waves have a high frequency and a very short wavelength. Okay. Now, this is another thing that's unique about light waves. Because they all go the same speed, that 300 million meters per second, it means that each frequency has a unique wavelength. And if you know the wavelength of light, you also know its frequency of that light beam, and vice versa. If you know the frequency, then you can figure out the wavelength. And the way you do it is just by plugging it into the wave equation. I'm not going to have you do this, but I do want to show you that it's possible. V, the speed of the wave, is always the speed of light, 3.0 times 10 to the 8th. That's this right here. And if, for instance, you know that the frequency of this particular light is 10 million hertz, 1 times 10 to the second hertz, 7th hertz, then you can solve for the wavelength, which in this case would be 30 meters, which is actually a very long wavelength for a light wave. So, and likewise, if you know the wavelength, 30 meters, you can figure out that the frequency is 10 million hertz, because V is always the same for all light waves. Okay, now how about perceiving different frequencies of light? It turns out that as humans, we can distinguish between one frequency of light and another. We can tell them apart. And the way we do that, you may already know this, is by color. We perceive different frequencies of light as being different colors. So red has a different frequency than yellow, which has a different frequency than green, and different than blue and violet, and so on. So every color in the spectrum that we can see has a different frequency and a different wavelength. However, as an introduction to the electromagnetic spectrum, there are colors of light that we are blind to. Okay, so red just happens to have a particular frequency and wavelength, but there are other colors which have longer wavelengths, lower frequencies than red, that our eyes have not evolved to detect. And likewise, there are colors of light which are out here beyond the violet that have shorter wavelengths than the violet that we can see, but they're still light, they're still colors, we're just blind to them. But not all animals are. So for example, birds can see in the ultraviolet, which literally means beyond the violet. So these colors out here, they're beyond violet, that's ultraviolet. And birds can see them. So this is a myna bird from Hawaii, and to us it looks like pretty much a flat black bird. But if we look at them through an ultraviolet camera, we can see that different patches on the bird reflect different frequencies of ultraviolet light. So to another myna bird, a myna bird looks like it's a variety of colors. It's got a pattern to it. Likewise, insects, many insects, bees and butterflies can see ultraviolet. And to us, what looks like a yellow flower looks like a multicolor flower to them, because different parts of the petals reflect different frequencies of ultraviolet light. And it kind of focuses their attention to where the nectar and the pollen is. So the flower has evolved that way to attract pollinators. And finally, snakes, they can see at the other end. They can see in infrared. Infrared means below the red. So at the red end, if you go below the red end of the spectrum, infrared, well, snakes can see that. And infrared is actually, we perceive as warmth. And since mice are warm-blooded creatures, a snake can see a mouse in a deep hole in the ground on midnight of a moonless night when it's completely dark in there, and it's too dark even for the mouse to see. The snake can see the mouse because it's glowing in infrared, because it's warm. It's kind of creepy, but it's also kind of cool in its own way. Okay, so that brings us to the electromagnetic spectrum. It turns out that we're not blind to just a small part of the whole spectrum of light. We can actually see just a tiny, tiny slice of it. We're blind to most of it. Visible light falls in this very narrow band right here. They've expanded it out so we can see what it is, but the actual part that we can see is just a skinny little slice right here in the middle. And all this, we're completely blind to it. But it's out there, it exists, and we do different things with it. We handle it different ways. So your lab activity is going to be to make a chart, make a diagram of this, basically copy something that looks like this that you find off the internet or get out of books, as a way to remember the details of the electromagnetic spectrum. This is stuff that you got to know, and it's basically just a bunch of information that is organized in this way. So now I'm going to go through these different bands of the electromagnetic spectrum and tell you a little bit about them. And you could use that information in the lab that you put together. Okay, so visible light here is in the middle, and above the visible light is the ultraviolet, and below the visible light is the infrared. Now, how do we remember which one of these has more energy? The one that has more energy is the ultraviolet. And one way to remember that is that ultraviolet light is the stuff that will give you sunburn. It actually has enough energy to start taking apart the molecules and proteins that make up you. There's enough energy to break those bonds. And that probably deserves a little bit of explanation. So I'm going to go back to this diagram here. We said before that light comes from electrons falling from high energy to low energy. But most things in physics can happen in reverse. So if a light wave comes in and strikes this electron when it's at a lower energy level, it gives it enough energy to lift it up to a higher energy level.